Okay, so this is the introduction to the rank plus nullity theorem, and it actually gets called something like the fundamental theorem of linear maps in linear algebra. It's a big theorem. In your book, it's called the rank theorem. It's on page 235 in section 4.6. But the proof of it in our book depends on pivots, about which the author never proved anything in the first place. So we're going to do a different proof, parts of which you're going to be held responsible for knowing. And as I think you're going to see, it's a good review of all these parts. So the rank plus nullity theorem. First of all, let's talk about those two words. So let's let the rank of a transformation be equal to the dimension of the range of that transformation. Okay, and we denote by small r. The nullity, its definition is it's the dimension of the kernel of that transformation. Okay, so here the claim goes. Suppose that T is a linear transformation and that V has dimension n, little n. Then the rank plus the nullity will always equal to little n. It's very interesting. There's not much in here that has anything to do with the dimension of the codomain, right? So to get yourself straight on what all those things are, let's remind you of that example we just did. If A was the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, if you remember, we did that example in the previous video to this one, and we showed that the kernel was this line through the origin, and therefore the nullity, which is the dimension of the kernel, would be 1. We talked about the range of that mapping. We showed it was the plane going through the zero vector that's normal to that vector. That was in this example. And a plane is going through the origin is a subspace of dimension 2. So that's what we're calling the rank, the dimension of the range of the transformation, right? Notice that 1 plus 2 is equal to 3. Who said I never got into numbers in this class? Also in the course of that example, I said, before we got into the nitty-gritty of how to pound out that the range was exactly a particular plane, that this theorem would have helped us predict halfway through that whatever the range was, whatever this space over here was, it was going to have dimension 2, because 3 minus 1, using the nullity being 1, and that's easier to find usually, 3 minus 1 is equal to 2. So that's the theorem that we're now talking about we can be able to use in the future to make that process a little bit easier, at least know what size dimension of something you're looking for. And a number of other applications. Okay, so we're going to do a proof that doesn't involve any pivots. All right, but it does, just as the book does when it proves this rank theorem in section 4.6, it assumes you've seen two theorems that we're going to need to go back to and prove, but kind of motivating why we would even look at them. They're really there in section 4.5 for you to use in section 4.6. All right, so the 4.5 theorem is number 10. It says that anytime you have more than one basis of a space, a subspace, then they have to have the same cardinality. And that's how we define the dimension of that subspace. I think we talked about this before spring break. We didn't get to a proof of it. Man, there was a reason. We needed a lot of machinery to get all the way into 4.5 before we could. Also, Theorem 11 on page 229. And this is pretty crafty or sneaky, depending on your point of view. That anytime you have a linear independent subset of a vector space, let's say the vectors are called u1 through um, that can be extended. So this subset can be extended into a basis of V. Starts with U1 through UM, and you build it up, you extend it with some more vectors until you get enough. So if V has dimension n, then it's got to be true that m plus r will have to be equal to that n by the previous theorem, right? Okay, so we're going to go back and prove those, but for right now we're going to use them to motivate why you would want to prove them in the first place. All right, so the proof goes like this. You start with a basis of the null space, right? Remember that's sitting in the domain, right? And it's got m vectors in it because the nullity is equal to m. Right, that was up here. By theorem 11 down here, this can be extended into a basis of the entire domain, u1 through um, and built on vectors v1 through vr, where r, the difference here, the number of vectors that you're extending it with, is equal to the difference between the dimension of the whole domain space V and its kernel, right? N minus M. Okay. What we need to prove is that R is in fact the dimension of the range space, okay? And to do that, what we're going to do is we are going to construct a basis. Can you see that here? We're going to construct a basis of the range space using these vectors, v1, v2 through vr, but not them exactly. We're going to use their images underneath the transformation. And we're going to show, well, you know, since they're images of vectors under the transformation, they belong to the range space, right? And we're going to prove that these guys are, they span the whole thing and that they form a linearly independent set, and therefore they will be a basis. And because of theorem 10, once we have a basis, and this basis has cardinality r, it's got r things in it, that will mean that the dimension of the range is equal to r, and that will give us our result. R will be equal to n minus m. Right, so this is m, this is r, this is n, or n minus m will be equal to r when we're done, okay? All right, so that's just the setup. So the next video is going to go into parts A and B, the proof of those.